Hi, this is Team 7, and this is our final presentation on a hair trimmer. The product description, as you can see, is just a trimmer that is used to cut hair. A broken down diagram labeling each part. Primary customers are generally at-home haircut trimmers or hairstylists who are using the trimmer to cut head hair. The secondary customers are hospitals who are using it to cut body hair for patients. Here's a fast diagram. You can see the key nodes. Here are fishbone diagrams for two different assemblies. As you can see from our analysis of the assemblies, a sequence 2 was better. Here's a functional component mapping matrix. Here is a bill of materials with some assumptions listed on the slides. Here is a quad chart, which defines each part by its functional importance and manufacturing cost. Here's a functional differentiation table, which defines which functions go into both and which go into a singular customer group. Here's a component commonality table, which defines which parts are platform parts used in both models and which are module parts that have to change. Here's our first component redesign, which removes a bunch of the parts that allows the trimmers to adjust its length, as medical hair trimmers do not need that functionality. Another component redesign that we did was designing the reciprocation adapter into a new material and making it more simple so we could reduce cost and make it easier to make. Here's a assembly sequence updated. For delayed differentiation, it actually follows assembly sequence 2 quite well.
Here's our manual assembly analysis of the primary product. You can see the assembly times are calculated for all 15 parts, and there's a total time in our efficiency. The chosen parts to redesign are the retaining clip and the blade length button. They had longer assembly times. They can be reduced, and the retaining clip is important for function and achieves the function of creating a safe device and a reliable device. And the blade length button is also very necessary because it allows for the length to be varied, which is important for our primary market, and has unnecessary features that we can change and take out. You can see here, this is the retaining clip. The before is on the left, the after is on the right. We made the clip symmetrical to reduce rotation needed to orientate the part when assembling. There's an alignment feature on both sides to align it with the blade and with the bottom case, and it's slightly wider to improve the handling. The blade length button was not symmetrical before, which made it more difficult to orientate when assembling, so this was changed. The part is slightly larger, so it hits that 15 millimeters that's important for handling times. And there's a plus shape on the bottom now, which allows it to line up more easily with the bottom of the case. Here you can see the times have been reduced with our new part changes, and the efficiency is increased by 5%.
Moving into the design for automated assembly phase, we have selected the blade subassembly, including the fixed blade, reciprocating blade, and blade cover to automatically assemble. We've chosen these parts based on the quad chart earlier in the presentation. They are parts of high functional importance, and they're not all necessarily expensive to manufacture, but as they are functionally very important to the rest of trimmer, we decided that these ones would be good to automate in order to achieve that kind of consistency that comes with automated assembly. Taking a look at the next slide, we see the blade cover first. Initially, the blade cover was designed with snap fits to snap directly into the rest of the trimmer, but this is something that's good for manual assembly and not so much for automated assembly. To change this, we decided to add screw holes where 2 screws could mount the blade cover onto the rest of the trimmer assembly. This can be done very easily with machines at very precise torques to not damage parts. Screws are fairly cheap. Overall, manufacturing of this part may be more expensive with the screws, but the cost of assembly is decreased significantly through the automatic assembly process. Moving on to the fixed blade on the next page. The fixed blade sits directly on top of the blade cover, and it doesn't move as it is fixed. It comes flat initially in the original design, but we have decided to add little walls and small bends on the side, on the top and bottom and the sides of the fixed blade. The walls are there in order to help prevent with overlapping during the vibratory feeding process. And then the small bends will help with orienting the part, as when it is flat, it isn't necessarily the easiest to get in the right direction because it is not symmetrical on the top and bottom face of the blades. Looking at the reciprocating blade, it's a very similar situation. There are slightly more pronounced bends that we added, and walls were also added to mitigate overlap during the feeding process. But overall, the rest of the process in the changes were the same between the two blades. Looking at some key dimensions of the redesigned parts of this, there are specific tolerances that we had to maintain during when we changed these parts, because we didn't change every face of all the parts, and they still work together even with our redesign.
Next, for our process selection, we considered the fixed blade, and going through the process selection matrix, we finally worked our way down to sheet metal working or machining as our primary processes. We selected sheet metal working as primary due to its lower cost, but a secondary process is machining to create a sharp blade. Next, we looked at the blade cover, and for our process selection matrix, we eventually found machining, injection molding, and blow molding as feasible processes. We eliminated blow molding due to the geometry, and we selected injection molding as it is low cost. Next, we look at our blade holder redesigns. So we made changes to include addition of a better draft angle, reduction of snap fits to make assembly easier, and to make injection molding more feasible. And we also include screw points in order to combine the parts more securely than the snap fits would allow for. Next, we looked at DfM Pro and determined what changes could be made to our redesigned part.
We can see the fixed blade had some redesigns as well. You can see all the pertinent dimensions. It was changed to have a slight bend, which you can see in the top left, which is to help with alignment and assembly. It's got some walls to avoid overlap for automated assembly, so it can be put on part hopper. And you can see we flattened the edge of the blade slightly so that post-processing is easier. So here you can see we took the fixed blade and we put it into hubs to calculate the price to create it. Before the design and after design, both with our analytical and hubs method, the price increased, and that's including profit margin for hubs. And this is partly because a lot of the features we added make the part more difficult to produce, but are important for assembly time.
For our product service system, we are going to provide customers with a subscription service where they are able to buy new blades that are delivered every quarter to their home. This way, they can always have nice, clean, consistent, painless shaves, and there will be a negative impact on the environment since they do not need to go out and buy a whole new razor when the blade becomes dull. They can merely just be replaced. For our conclusions and design critique, some of our benefits, we increased the ease of assembly and its cost. And the pros of the design, we allow for more product variability while decreasing cost to certain customer groups. Some of the cons of our design is that it's increasing complexity and manufacturing costs to some of the components to aid in assembly cost. And then reflection is that we would look to a product that would be easier to DfM and DFA, as well as looking for changes that should be made instead of changes that could be made.